Hey guys, this is Mrs. Lyons with a video on polarity. We're going to talk about bond polarity, molecule polarity, and then we're going to talk about intermolecular forces that result from different polarity, different polar molecules versus nonpolar molecules. And then we're going to talk about some properties of substances that are based on the strength of the intermolecular forces. Okay, so to start off, we want to talk about bond polarity. And bond polarity is based on the electronegativity values of elements in the bond. Remember, electronegativity is defined as the attraction an element has for the electrons shared in a covalent bond. Okay, so on the back of your periodic table, there is a list of the elements and their electronegativity values. Okay, and if you look at this list, fluorine has the highest electronegativity value of all of the elements on the periodic table, which means that no matter what bond fluorine is in, the electrons in that bond are going to be more attracted towards the fluorine atom and less attracted towards the other atom in the bond. Okay, so let's just look, and if you notice, on the table it tells us, and we're only going to talk about polar and nonpolar right now. Okay, I'm going to abbreviate electronegativity, EN. Okay, so if the EN difference, if the electronegativity difference between the atoms is 0 to 0.49, we call that a nonpolar bond. So basically what that means is that the electrons in that bond view both of the atoms equally. Okay, so the electrons aren't going to spend more time around one atom or pulled towards one atom versus the other. Okay, if that electronegativity value difference is greater than 0.5, what we say is we have a polar bond. Okay, and what that means is the electrons are going to be more attracted to one of the atoms versus another. Okay, so let's just look at a couple of examples. Let's look at, we're going to look at hydrogen and chlorine. We're going to look at hydrogen and carbon. And we're going to look at oxygen and hydrogen. Okay, so if I look at my electronegativity table, all right, hydrogen has an electronegativity value of 2.1. I'll put that for all three of those. Okay, chlorine has an electronegativity value of 3.5. Carbon is 2.5, and oxygen is 3.5. Okay, so to determine if these bonds are polar or nonpolar, what we do is we take the difference. Okay, so 3.5 minus 2.1 is 1.4. Okay, that's greater than 0.5. This is a polar bond. What that means is since chlorine has a higher electronegativity value, the electrons are going to spend more time around the chlorine than they are around the hydrogen. And if you remember when we did this back last semester, we talked about this idea of a dipole where we draw the positive plus sign over the lesser electronegativity element, the element with the lesser electronegativity, and draw the arrow towards the element with the higher electronegativity value. Okay, so this bond is a polar bond. Okay, it's unevenly shared electrons. Okay, carbon hydrogen, if we take the difference here, the difference is only 0.4. Okay, so what that means is that this is a non-polar bond. Okay, so even though those two elements are different, they're not different enough that the electrons are going to spend more time attracted to one of the atoms over the other. And then finally, oxygen and hydrogen is just like chlorine and hydrogen, actually 3.5, so a difference of 1.4. So the same idea here, that would be a polar bond. Okay, now more importantly than the polar bond, because we're always going to be looking at molecules. Occasionally we'll have a molecule that just has two atoms in it, but most of the time we're going to be looking at compounds. Okay, and when we look at a molecule, okay, we have to look at the molecule as a whole to determine if the molecule is polar or not. Okay, so if we have a polar molecule, so in polar molecules, there's a partially positive portion of the molecule and a partially negative portion of the molecule. So let's look at water as an example. Okay, water has an oxygen connected to two hydrogens, and we have two lone pairs of electrons on the oxygen atom. Okay, now up here we said that the oxygen-hydrogen bond is a polar bond. And if we were going to draw a dipole here, we would put the plus sign over the hydrogen and draw the arrow towards the oxygen because it's more electronegative. If we did that with both of these bonds, okay, in this water molecule, what we would see is the oxygen portion of that molecule, okay, is more negative. It's not completely negative, but like it would be if it was an ion. But what we say is that oxygen, and we draw this little kind of a cursive looking D, which means partial. The oxygen is partially negative, and the hydrogens are partially positive. Okay, so that's what we're talking about when we're talking about a polar molecule. Okay, and I'm going to give you a different way to determine if a molecule is polar rather than figuring out the electronegativity of all of the different elements and bonds. Okay, so here's what we would look for to determine if a molecule is polar. Okay, so a molecule is polar if, and there are two ways we would determine a molecule to be polar. A molecule is polar if there are one or more lone pairs of electrons on the central atom. Okay, so water, H2O, is a perfect example. We've got these two lone pairs of electrons on the central atom. That makes water a polar molecule. Another example of a polar molecule, we would have, and for this, in this unit, we are going to draw the structures for you. You won't have to draw them. But you should be able to look at them and see. Okay, so H2S, very similar to H2O, has two lone pairs of electrons on the central atom, making this a polar molecule. Okay, now I said there were two ways to determine. So this was the first way. The second way is to look at the symmetry of the molecule. Okay, and what we mean, the way that we want to think about symmetry, we're going to look at all of the atoms attached to the central atom. Okay, if there are different atoms attached to the central atom, the molecule is polar. Okay, so let me flip a page or two over. All right, so let's look at some examples of this. Okay, there we go. All right. So I'm going to draw several molecules, and we're going to look at these, and we're going to determine, are they polar molecules or are they non-polar molecules? All right, so okay. So here are a number of examples of molecules. Okay, so I want to determine, are these molecules polar or not? Okay, so let's just kind of look at the group of molecules. So we have CH4, we have NF3, we have BH3, we have CH2O, and we have CO2. Okay, so the easiest way to determine if a molecule is polar is to pick out the ones that have these lone pairs of electrons on the central atom, only on the central atom though. All right, so right off the bat, NF3 is a polar molecule. Okay, none of the rest of these have lone pairs of electrons on the central atom, so we need to think about that second condition. Does the central atom have different things connected? Okay, so CH4, everything attached to the central atom is the same. That means this is going to be nonpolar. Okay, and if you think about that, that makes sense, right? Because polar means there's a part that's more negative and a part that's more positive. Well, these hydrogens are all the same. So that they're not going to be polar because the electrons are shared equally throughout that molecule. Okay. BH3. Okay. Again, no lone pairs. All three things attached to the central atom are the same. So that's another nonpolar molecule. All right. What about CH2O? Okay, C is the central atom, so no lone pairs, but we have hydrogen, two hydrogens attached, and an oxygen. So the atoms attached to the central atom are different, which makes that molecule polar. And then finally, carbon dioxide, CO2, no lone pairs of electrons. The atoms attached are the same, so that makes this a nonpolar molecule. Okay. Now, why do we care? All right, we talked about this last semester just in determining if molecules were polar or nonpolar, but we kind of stopped short. We did talk a little bit about intermolecular forces, but we kind of stopped short in terms of talking about the properties of molecules and compounds based on their polarity and their intermolecular forces. Okay, so intermolecular forces. We refer to these as IMFs, intermolecular forces. Okay, intermolecular forces are forces between neighboring molecules. Okay, what that means is I'm going to have, if you think, let's just kind of do the opposite. The opposite of intermolecular forces are intramolecular forces. And these intramolecular forces, we know those by the name. Those are just bonds. Okay, there's bonds within a molecule. Okay. So when we drew these compounds up here and we drew these bonds, those are intramolecular forces. Intermolecular forces describe how neighboring molecules interact. Okay, there are three intermolecular forces. All right, we have London dispersion forces. These are the weakest of the IMFs. All molecules have London dispersion forces. Okay. All molecules are going to have London dispersion forces. What a London dispersion force is, just to refresh our memories, is it's a momentary dipole. Okay, and what that means, another way you might see it is an instantaneous dipole. All that means is that at any point in time, because the electrons are always moving, there might be more electrons in one area of the molecule. And what happens is, if you have this momentary place where there's more electrons in the molecule, what's going to happen is a neighboring molecule, the electrons in that molecule are going to be repelled because like charges repel each other. Okay, so we call it a momentary dipole. Okay, it doesn't happen. It's not a very strong force. It's a very weak force, in fact. And it's instantaneous. It's not a lasting dipole. Okay, so London dispersion forces happen in all molecules. Okay, in nonpolar molecules, London dispersion forces, LDF, are the only intermolecular force. Okay, so if you identify something as nonpolar, and I say, what are the intermolecular forces in this molecule? You would say London dispersion forces, and that is all. Okay. The second type of intermolecular force is called a dipole-dipole interaction. Okay. And what a dipole-dipole interaction is it happens in polar molecules. Okay, so for example, we had water, okay, and we said that water, this part of the molecule, the oxygen where the electrons are, is partially negative, and the hydrogens are partially positive. What happens is then these molecules are going to line up with the positives and negatives attracted to each other. Okay, so the arrangement of these molecules is gonna take place in such a way that the positive portion of one molecule lines up with the negative portion of another molecule. Okay, so dipole-dipole interaction happens. Okay, all polar molecules have dipole-dipole, and I'm going to abbreviate DD, dipole-dipole forces. Okay, these are stronger than LDF, but not as strong as our next type, as hydrogen bonding. Okay, so let's look at another example. Let's say we have this this molecule. Okay, because this oxygen has the extra electrons around it, this would be partially negative. So what would happen is, and these would be partially positive. What happens is then the hydrogen from a neighboring molecule, the hydrogen that's partially positive would be attracted to that oxygen. Okay, so dipole-dipole interaction is a little bit stronger than London dispersion forces, but not as strong as our final intermolecular force, which is called hydrogen bonding. Okay, hydrogen bonding occurs between a hydrogen that is attached to an oxygen, a hydrogen that is attached to a nitrogen, or a hydrogen that is attached to a fluorine. Okay, so when we look at our molecules, we have to have this situation. And the reason that these hydrogen bonds are so strong is oxygen, nitrogen, and fluorine have very high electronegativity values. Okay, so that it's a dipole. It's like the dipole-dipole, but it's a super dipole-dipole. It's stronger than just an ordinary dipole-dipole because of these three elements that are involved. Okay, hydrogen hydrogen bonding is what makes water have many of the properties that it has. Okay, hydrogen bonding is the strongest IMF. Okay, another example of hydrogen bonding would be in ammonia, which is NH3. Okay, we have a nitrogen attached to three hydrogens. What's going to happen is in a neighboring molecule, okay, we would have an attraction between the hydrogen and the nitrogen on another molecule. This is what a hydrogen bond is. Okay, it gives some of these compounds their special characteristics. Okay, hydrogen bonding only happens in these three circumstances. Okay, so let's look at a couple of examples, and then we'll talk about why we care so much about these intermolecular forces. So let's say we have I'm going to draw several molecules. Let's see. And okay, I think that's good. Okay, so 4 molecules. Let's take a look at these. Okay, first thing we need to do is determine, are they polar or nonpolar? Okay, actually, the first thing you could do is you could say, oh, I know every single one of these molecules has London dispersion forces. Okay, that's the weakest force. All molecules have it. Okay, now we have to decide which of these molecules are polar and which of these molecules are nonpolar. Okay, so remember we said if we can find the lone pairs of electrons, that tells us a molecule is polar, right? So this molecule is polar right off the bat. And water, we've got 2 lone pairs of electrons, so that's polar also. All right. What about this? See, no lone pairs of electrons, but notice I've got chlorine and hydrogen, so I've got 2 different things attached. So this is polar. And then BF3, there are no lone pairs of electrons. Everything attached is the same, so this is a nonpolar molecule. Okay, now, so this BF3 is done. It's nonpolar. The only force it has is London dispersion. All right. All of our other molecules, so you can just go right through right now and say all of these molecules have dipole-dipole, the 3 other remaining molecules, because they're all polar. Okay. Then we have to look for that special circumstance of hydrogen bonding. Okay. So we have hydrogen in this compound, but it is not attached to an oxygen, a nitrogen, or a fluorine. So this molecule, the strongest intermolecular forces are dipole-dipole. All right, what about this one? No hydrogen in that one, so that's pretty easy. So that one, the strongest force is dipole-dipole. All right, and then finally we have water. Water does have that hydrogen attached to an oxygen. So this one has hydrogen bonding. Okay, so it has all 3 of our intermolecular forces involved. Now, why do we care? Here's why we care. Many of the properties that we talk about, so things like surface tension, things like evaporation rate, melting point, melting temperature, boiling point. We can predict these properties based on the type of intermolecular forces. Okay, so surface tension, remember we talked about surface tension? I showed you the little water bug that just kind of scoots across the water because water has such a high surface tension. Okay, so surface tension, the stronger IMFs have greater surface tension. Okay, so that would mean that water, because it's got hydrogen bonding, would have the greatest surface tension. And then the 2 polar molecules would be next. And then LDF, the BF3, would have the weakest, the least amount of surface tension. Okay, evaporation rate. This is how quickly something evaporates. Okay, so the stronger IMF, stronger IMFs have longer evaporation rates. Okay, meaning it takes them longer to evaporate. Okay, so again, water would take the longest of these 4 compounds to evaporate. Let's see, the nonpolar BF3 would have the quickest evaporation rate. And then finally, melting point and boiling point, these 2 go hand in hand. Something that has a high melting point is also going to have a high boiling point. The stronger the IMF, the higher the melting point and boiling point. Okay, so those are just some things to keep in mind as we are looking. We're going to give you these compounds and we're going to say, okay, which one would have the higher melting point? We might ask you, which one of these could I put more drops on a penny with? Remember we did that, drops on a penny. So we would expect something with hydrogen bonding to be able to put more drops on a penny. Okay, so those are the kinds of things that we will ask you about. All right, so I think that pretty much is a wrap on polarity, bond polarity, molecule polarity, intermolecular forces, and how those intermolecular forces affect some of the properties of matter. All right, I hope that was helpful for you. Have a great day and take care of yourself.